For the BEAST project, the sensor we were given was an accelerometer. So whatever we're going to control has to change velocity, and that change is what we're measuring for control purposes. So let's make a rocket. We're gonna try to make a two-stage rocket. Each stage will be a pressurized soda bottle, and that will be unsealed in order to fire the rocket upward. So how do we unseal it? Well, there's this thing called a solenoid, which is basically an electronically controlled valve. The solenoid we chose to use was the cheapest one we could find on Amazon because we are in college, and that takes a 12-volt power supply. The microcontroller we're using is an Arduino Nano because it can take also 12 volts as a power supply and output 3.3 volts, which we need for the accelerometer. But it can't output 12 volts, so still we're left with the question of how we're powering the solenoids. For that, we can use a transistor. A transistor is basically an electronically controlled switch. So we can use the Arduino Nano to control the transistor, which takes 12 volts, and we'll put it to the solenoid. A rough actual diagram of these basic electronics would be this. We've got our 12-volt power, an Arduino Nano, which is feeding 3.3 volts to the accelerometer, and each solenoid is given 12 volts, and the transistor's connected to the Arduino Nano, and that will close the circuit and actually power it, which looks an awful lot like this in actuality. We have Arduino Nano, transistors, batteries not attached to either of the solenoids, but this is the brain of the entire rocket ship. So now the question is, how do we control something like this? Well, we use code. The code for this looks like this. Now, the first block up here tells the computer what all the variables are. These are basically names that we'll reference later in the code. This block is a quick function that will map a given value that is in between a minimum and a maximum to an output minimum and maximum. And then this is the setup code. Now, initially, all we do is tell the Arduino which pins we want to use. We're going to set a reference for the ADC because the Arduino ADC can actually take multiple values, and instead of the default 5 volts that the Arduino will normally use, we want to use 3.3 volts so that we have the full range of the output of the sensor. This line just lets me talk to the computer for debugging purposes. Now, this is where things get interesting. This chunk here calibrates the sensor. Ordinarily, the sensor and the Arduino don't know which way is up, down, left, or right. They're completely unoriented. What this will do is grab a series of 45 data points from each pin on the sensor, combine them, average them, and then set that as the 0 acceleration for each axis. Then it'll open that first solenoid tank so that we have a calibrated sensor before we send ourselves up into the air. Now, the running loop of this is also interesting. All we're doing is reading each value from the sensor, then we're going to map it to a point that is an actual gravity value instead of 0 to 1024 because the Arduino comes with a 10-bit ADC, and we calculate the net acceleration. Each acceleration from the X, Y, and Z pins on the accelerometer are effectively acceleration vectors. So the way that we do that is we square each value, and then we root it, and that will give us the net acceleration, which lets us do something fairly clever. Because the net acceleration is always positive, and we know that in order to be accelerating upwards, the acceleration in the Z has to be greater than 0, what we can do is say, if your acceleration is less than 0.2 Gs, and the acceleration in the Z-axis is greater than 0, then we want the second stage to fire. What this does is it prevents the rocket from flipping upside down and then sending itself into the earth. This is the line of code that opens the second solenoid, and this is for debugging, which I will again show you in a second. And now's where everything comes together. I've got the electronics wired up with a battery and situated how they will be on the rocket. I've got my computer attached to it, I've got the code, and I have an actual output of what is going on. Now, something additional I'd like to point out. When I did the logic for what would trigger the sensor, we actually have a little bit of a band where the net acceleration has to be less than 0.2. That's because if we look here, sometimes we get a little bit of noise in the signal because it's so sensitive, and I get a acceleration of 0.01 G. As you can see, this is not moving because I'm not insane enough to put a pressurized air canister under it and fire that off in my house. But it does show up here, which could be a problem. So that's there to actually filter out any bad data. Now, if I switch this on and reset our lovely little board, what will happen is it should calibrate. Let me know that it's calibrated. And then if we turn it on its side, you can see that currently it thinks that it's accelerating, which is letting us simulate what would actually be happening if the rocket were flying. Now, the reason that it thinks it's accelerating is because we calibrated it. So we told it which way is up, and gravity is an acceleration. Now, if you watch and we turn this back up and down, it will say that it got triggered, and we can check that it got triggered because I actually have a 12-volt solenoid here. That was the little click you heard earlier when everything booted up. We can unplug it from the first solenoid. This might get a little shaky, but we can unplug it from the first solenoid and plug it in to the second solenoid, and you'll actually still hear a click, and that means that they're both energized. So everything works, and we just need to add the pressurized bottle.
The bottom one is way better.
Yeah.
Look at this.
Okay.
Alright.
Flipping the switch.
Wait.
I don't know how long it's gonna take to calibrate.
Shoot, I was supposed to. Yeah!
So, why didn't this work? Well, the biggest reason is that pneumatics are really, really hard to make, and that's why you have professionals. We basically just tried to epoxy a bike valve into a plastic bottle, and it almost worked a few times. We actually had a bottle that got up to about 40 PSI, and then we kept pumping it, and then it stopped being able to hold air. So that's the one big problem. Problem number two is the solenoid valves that we had, well, cheap as hell and also deliverable on Amazon, both of which, very good for us, have very, very tiny throughput holes. So the amount of thrust you can actually get out, not that big.
However, there were a lot of things that we did try to fix to mitigate some of these issues. For example, when we tried to fix
You want to bring it up?
yeah. when we tried to fix the bike pump issue, we did try JB Weld, which worked for about 20 PSI, then it gave away the next day. We then talked to a professor and we tried to fix it using silicone, non-flowable silicone, which also worked for about 40 PSI and then it gave away. We tried, as you can see, with all the white paint, using Flex Seal on top of the silicone. It also did not work. So there were a lot of things that we tried and they still didn't work. So we kind of gave up on that. But thankfully, we have proof of the actual electronics working, and I believe the 3D print came out pretty well.
All right.
So really, the only thing accelerating was my will to live accelerating down. Goodbye.
Goodbye.
Rocket launch in 3, 2, 1, maybe. We succeeded.